Okay, starting chapter 2. Atoms, molecules, and ions. What seems to often happen in a chemistry course is that the chapters kind of alternate between lots of math and very little math, and lots of math and very little math. And so this is our break from math. There's very little math, just a little bit of adding and subtracting. Atoms, molecules, and ions. I am going to be not covering some sections of this in the lecture. They show up in the Learn Smart assignment, and you have to answer questions about them, but I'm not going to test you. There's a bunch of descriptions of very important historical experiments. I'm not going to test you on those. You should read through it and answer the questions in Learn Smart, but I'm not going to go over them in lecture because that's not really part of this class. That's part of 1A, and you'll get that all there. But this is something that is important. We can't really understand chemistry without talking about Dalton's atomic theory. And Dalton's atomic theory, the different points of it can be written in different ways. And so this is a graphic I pulled from somewhere else. It doesn't match up exactly with how they specify Dalton's atomic theory in your textbook. I'm not going to ask you to regurgitate Dalton's atomic theory. We just need to absorb the concepts. So Dalton, I believe this was back in the 1800s, early 1800s, was the first modern scientist to propose atoms. This idea came from a couple of guys back in ancient Greece, but then people didn't believe them, and so then we got all sidetracked for centuries. And Dalton comes around, and he's proposing this atomic theory. Each element is composed of extremely small particles called atoms. So here in this graphic, we're representing an atom of the element oxygen as a red ball and an atom of the element nitrogen as a blue ball. All atoms of a given element are identical, but the atoms of one element are different from the atoms of all other elements. So every oxygen atom is the same as every other oxygen atom. No differences. Every nitrogen atom is the same as every other nitrogen atom, but nitrogen atoms are different from oxygen atoms. And here I think the Lego analogy is very good. I'm going to draw a picture. It's going to be ugly. Do it anyway. So the oxygen atom is like one of those little 2x2 Lego bricks, right? You go through the pile of Legos. We've been collecting Legos from, well, my oldest is 23, so we've been collecting Legos for a long time. We have piles and piles and piles of Legos. You can dig through the Legos. You can find lots of little red bricks like that. They're all the same, right? They're all the same. All the oxygen atoms are the same. And then there's nitrogen atoms, and they're blue. And maybe they're not 2x2, I don't know. Maybe the nitrogen ones are the 2x4. Different Lego brick, different color, different shape. They're different. But all the nitrogen atoms are the same as each other. Okay? Atoms of one element cannot be changed into atoms of a different element by chemical reactions. Okay? When Dalton first proposed this, he left out the biochemical reactions. He just said you can't change atoms of one element into atoms of another element. Well, this was before nuclear chemistry. We now understand that you can change an atom of one element, into an atom of another element. You can change lead into gold. It's not financially profitable. It costs way more than just going out and looking for gold. Yeah. So that's why we don't do it. Alchemists spent years and years and years, many people spent their lives trying to turn base metals into gold so that they could get rich. Nuclear reactions allow us to do that, but in terms of chemical reactions, it's not possible. So for Legos, you cannot change this red Lego brick into a blue Lego brick when you're playing with Legos, can you? You can't do it. Now, if you wanted the element that was the 2x2 blue brick, Could you take a hacksaw or a bandsaw and cut it in half and kind of make it work? Could you melt these down and remold them into the shape you wanted? That's the equivalent of nuclear chemistry. Okay, that's bringing out big tools, way more effort than is worth it, right? So we're talking about chemical reactions, playing with Legos with your hands. You can't convert one brick into another. In a chemical reaction, atoms are not created, they are not destroyed. All the atoms that you start with are all the atoms that you end up with. What happens in a chemical reaction is they just get rearranged. It's taking one little Lego structure, pulling it apart, and sticking the bricks back together in a different way. That's what a chemical reaction is. Taking the atoms apart and putting them together in different combinations. So compounds are formed when atoms of more than one element combine. So here we have one, okay, anybody see the typo on there? I did not write this. What's wrong with that? They labeled the red ball nitrogen. Yeah, I see these things and I just can't even help it, and oh, good grief. Okay, this is oxygen, and that's nitrogen. Okay. One oxygen plus one nitrogen gives us no. That's yelling, right? Capital N, capital O. No. It's nitrogen monoxide. Nitrogen monoxide is just one of these Lego bricks and one of those Lego bricks stuck together. Okay? And when we have a compound like this, we've talked about compounds versus mixtures. Compounds have a definite or fixed composition. Every molecule of no has one nitrogen and one oxygen atom stuck together. Any questions? So in my mind, all of matter is a bunch of Lego bricks. Here's another illustration. Chemical reaction between oxygen and carbon. So here we have oxygen. Oxygen is not found as individual atoms. It's actually found as these little molecules. But the oxygen will react with carbon atoms to form carbon dioxide. Every carbon dioxide molecule has one carbon atom and two oxygen atoms, and they're always the same. And so when we have this chemical reaction, the number of oxygen atoms that we started with 2, 4, 6, 8, right? And over here, how many red balls? 8. None of them disappeared. None of them appeared poof out of thin air. We started with 4 black balls, we end up with 4 black balls. We start with 4 carbon atoms, we end up with 4 carbon atoms. No atoms are created or destroyed in a chemical reaction. They just get rearranged. Okay?